Let's see what we can do with this. A 1,125 kilogram car and a 2,250 kilogram pickup truck approach a curve on a highway that has a radius of 225 meters. At what angle should the highway engineer bank this curve? I did not know what this meant earlier, so I just thought back to like incline planes, because like angle and road. But this is a bank. It's like so you go drive, and you aren't exactly like completely level with the floor, right? Like your tires are not like that, flat on the floor. Your tires are like this. They're tilted, and it's a banked curve, so it's curving. Oh yeah. Just in case, because that's going to be popping up later. Bank this curve so that vehicles traveling at 65.0 miles per hour. Why? Can safely round it regardless of the condition of their tires. This here tells me no friction. Should the heavy truck go slower than the lighter car? Well, we have two questions here. I think it's fair enough to split them off. So we need an angle, and we need this dearest theta. Oh, that's a poor theta. I don't care if if it looks like a phi. Boom. Theta. Good enough. You know it. You know it's there in spirit. We want an angle. We have a car. Like, let's just call this box a car because clearly I can't draw. And we have a box going on a curve. Boom, boom. At 65.0 miles per hour. Freaking annoying. So let's just do that conversion real quick. 65.0 miles over 1 hour. It's 1,609.34 meters. Sorry, I hate using a mouse, but we're living with it. For every 1 mile and for every hour there is 3,600 seconds, which is going to get you 29.1 meters per second as our velocity. Nice. We might want to keep that for later. Let's just move that over there. Like, you guys, we don't need you. Not anymore. Goodbye. Velocity. Boom. Okay, so we have our velocity. We have the centripetal force problem, which I probably should have said a little earlier, because we're going around in a circle. Yay! So, recalling centripetal force, it's basically you are... Oh, frick. I really need a better color. Oh, no, that's not even it. So you are here, and centripetal force is your force basically towards the center. Your velocity, that's going this way, and this force makes sure that you are going to stay on this track. If you go up a bit, you go right, and then you'll just keep on going on in this circle until the curve ends. But this just seems like a bit of a curve, so we'll only look at this part of the circle. Boom, 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 boom. Centripetal force. If you remember, mass times velocity squared over radius. Derivation's weird. And with the way this is said, there is no mention of a specific car or a specific truck or a specific other vehicle, so that clues to me that we might not need this mass. The radius, we know. 225 meters. Velocity, we just got. We might want to keep this in the back pocket. So we have our dearest boxcar, let's say. And normal force. Here we are. Normal force normal. I mean, that's how I do it. Force normal. And with this, we can also figure out a y component and an x component to this force. Normal force normal x, force normal y. If you want a trig proof, then boom, also theta. I'll get another color. And we also know that this has some mass. So this will go down as your force of gravity. Yippee. Now, if we want this car to stay in the center, and not, oh my god, and not absolutely crash, like in going to the center or like getting off the road, we need this like centerpiece to stay in the center. That will be pretty important. Now, this centerpiece is basically determined by your gravity and this y component of your normal force. So we need this normal force, which is positive, to be, when subtracted by this gravitational force, to be equal to 0. So that way it stays in this like center position. Hold on. I'm indecisive with colors. I'm sorry. So we know that the forces in the like y direction will be our normal force in the y direction minus our force of gravity, which is also in the y direction. And we need this to be equal to 0. Let me just move this. We can rewrite our normal force of y as our normal force times cosine theta, because this is normal force, this is y, cosine is adjacent over hypotenuse. So cosine times hypotenuse gets you adjacent. Who knew? So normal force times cosine of our mysterious angle theta minus our mass times gravity, because that's what your force of gravity is. So from this, we can figure out that our normal force times cosine theta is equal to our force of gravity, and we can also figure out that our normal force, oh my god, that our normal force is our mass divided by this angle. Wow, a shocker. On an inclined plane, you'd think it would be mass times gravity times cosine theta, because you need to stay on this plane. But that is in terms of like this direction. If you try to take the like FG cosine theta here, you're missing out on this FG sine theta. And if you try to make the normal force equal to this gravitational cosine theta force, they'll cancel out, and you won't even have anything going to the right. These are like parts of the normal force. So if you get rid of that, you get rid of those two. So if you try to force the normal force to equal force of gravity times cosine theta, you're sliding down. You're having that car tumble. You're not going around the corner. You've wasted $40,000 and also your AP score. I'm sorry. Let me clean that up a bit. So boom, normal force equals this mass gravity over cosine theta. I sure wonder if this will be helpful soon. Let's move that to the side. Let's make it smaller so that way we have like all our cool things in here. And I'll leave that there, why not? So we have our normal force, right? But we also have our centripetal force. Our centripetal force pointing towards the center. Like, that's what I try to draw over here. Like, this is your center. This is your centripetal force going over to the center always, because if you keep on turning, you'll just enter a new intersection with your normal force in the x direction pointing towards the center. Hopefully that makes sense. This x component will always be going to the center, no matter where on the bank you are. So we can use this equation now. So we have normal force x equals mass velocity squared over r. If you want the x, like your x normal force with an angle, you use sine because it's the opposite of the angle. So we have normal force times sine theta equals this. I probably should have just done that earlier. I'm so sorry for my handwriting, guys. I'm not used to a mouse. That looks like a 3. I'll fix that. Boom. And we've already figured out what our normal force is, so let's plug that in, why don't we? Boom. 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 Let's drag that over. Mass times gravity, cosine theta. Sine theta equals mass velocity squared over r. I see two masses, we can get rid of them. Same thing on both sides. I have a g on top, and I want all my angles on the side, so I'll move it. So I'll divide both sides by gravity. So it's now down here. And now I'm left with sine theta equals cosine theta. And if you know what sine over cosine is, then good job. It's tangent theta. Oh my god. Tangent theta equals this beautiful thing. And if we want the theta itself, we need to get it out of this tangent. We need to take the inverse of this tangent, which is arctangent. Yippee. Oh, wait, wrong order. My bad. Theta equals arctangent of velocity squared, which we said earlier was 29.1 squared over our gravity, which, for the sake of convenience, 10. If the AP exam lets you say gravity equals 10 meters per second squared, I'm going to use it. It's a lot rounder that way. And our radius of 225. And we get theta equals, I don't know why I decided to show you this, but yeah, 20.6 degrees. Yippee. So we answered the first part. Now second part. Should the heavy truck go slower than the light car? Actually, hold on. Let me clean this up a bit. Hopefully you got 20.6. I know that's a bit of contention right now. Boom, boom. Sorry. Here we are. Let's look back at our centripetal force. Centripetal force, mass velocity squared over r. we have a defined radius. We have defined masses, so we cannot change either of those two. If you change this velocity, if the heavy truck decides to go slower, then this whole centripetal force thing is going to be completely messed up. If you go a little less, then oh no, you're going to just freaking fall down. If you decide to speed up, then you're already out there. So even if the heavy truck decides to go faster than the lighter car, it's still going to end up the same fate of tumbling into the off-road, hopefully keeping the person inside alive. So no, don't go slower. The velocity should also be the same, so that way centripetal force stays the same, so that way this whole bank functions. Actually, I'll move this down here. No. As a car and truck round the curve at 65.0 miles per hour, which we already found earlier, 29.1 meters per second, find the normal force on each one due to the highway surface. Oh boy, we have our normal force equation right here, all prepped and ready. And they want to know the car and the truck. We might want to use mass for this one. So we have normal force of the car, which equals our mass of 1,125 times gravity of 10 over cosine of 20.6 degrees. To save you the pain of going over there, it is 12,000, technically 12,000 newtons. Technically like 12,020, but we're given 3 significant figures, so. And if you wondered what the normal force of the truck would be, the truck, which has double the weight, double the mass, sorry, weight and mass are used too colloquially, similarly these days. So it's just double that. So 2 times the normal force of your car, and that gets you 24,000 newtons. Like 24,030-ish. Like it's in the Desmos, but I hope you guys trust me. You can also plug and chug. Maybe watch this again. You need to stay at this point, but you also need this acceleration in order to go to the center thing is weird. Because if you just look at this, then you'd be convinced that this thing is going to hover over to the center. But we have that velocity of 29.1 meters per second going that way. So it's going to go in a curve with this force, with this velocity, and this tuned centripetal force. Hopefully that makes sense. If you find any errors, please let me know. Thank you.